How and when did our universe begin? How did it get to look like this? How will it end? Humans have been discussing these questions for as long as they've been around, without ever reaching much agreement. Today, cosmologists are working hard to find the answers. But how can anyone hope to find concrete answers to such profound questions? And how is it possible to explore and study something as huge as the universe, most of which we'll never be able to reach? The answer is light. And although light from distant parts of the universe can take billions of years to reach us, it carries 6 unique messages that, when put together, can disclose an amazing amount of information to astronomers who know how to look for it. Just as sunlight can be split up into the familiar rainbow, splitting the light from distant objects exposes different patterns of colors depending on its source. This distinctive light barcode can reveal not only an object's composition, but also the temperature and pressure of its constituent parts. There's even more we can discover from light. If you've ever stood on a train platform, you might have noticed that the train sounds different depending on its direction, with the pitch ascending when it approaches you and descending when it speeds away. But this isn't because the train conductor is practicing for a second career. Rather, it's because of something called the Doppler effect, where sound waves generated by an approaching object are compressed, while those from a receding object are stretched. But what has this to do with astronomy? Sound does not travel through a vacuum. In space, no one can hear you scream. But the same Doppler effect applies to light whose source is moving at exceptional speed. If it's moving towards us, the shorter wavelength will make the light appear to be bluer, while light from a source that's moving away will have a longer wavelength, shifting towards red. So by analyzing the color pattern and the Doppler shift of the light from any object observed with a telescope, we can learn what it's made of, how hot it is, and how much pressure it's under, as well as whether it's moving, in what direction, and how fast. And these 6 measurements, like 6 points of light, reveal the history of the universe. The first person to study the light from distant galaxies was Edwin Hubble, and the light he observed was redshifted. The distant galaxies were all moving away from us, and the further away they were, the faster they were receding. Hubble had discovered our universe is expanding, providing the first evidence for the Big Bang theory. Along with the idea that the visible universe has been constantly expanding from a densely packed single point, one of this theory's most important predictions is that the early universe consisted of just 2 gases, hydrogen and helium, in a ratio of 3:1. And this prediction can also be tested with light. If we observe the light from a remote, quiet region of the universe and split it, we do indeed find the signatures of the 2 gases in just those proportions, another triumph for the Big Bang. However, many puzzles remain. Although we know the visible universe is expanding, gravity should be applying the brakes. But recent measurements of light from distant dying stars show us that they're farther away than predicted, so the expansion of the universe is actually accelerating. Something appears to be pushing it, and many scientists believe that something is dark energy, making up over 2/3 of the universe and slowly tearing it apart. Our knowledge of the behavior of matter and the precision of our instruments means that simply observing distant stars can tell us more about the universe than we ever thought possible. But there are other mysteries, like the nature of dark energy, upon which we have yet to shed light.
The city sky is frankly rather boring. If you look up at the patches of murk between buildings, you might be able to pick out the Big Dipper, or perhaps Orion's Belt. But hold on, look at that murky patch again, and hold out your thumb. How many stars do you think are behind it? 10? 20? Guess again. If you looked at that thumbnail-sized patch of sky with the Hubble Space Telescope, instead of points of light, you'd see smudges. These aren't stars. They're galaxies, just like our Milky Way, cities of billions of stars, and more than 1,000 of them are hidden behind your thumb. The universe is bigger than you can see from the city, and even bigger than the starry sky you can see from the countryside. This is the universe as astrophysicists see it. with more stars than all the grains of sand on Earth. By staring up at the stars at night, you've taken part in the oldest science in human history. The study of the heavens is older than navigation, agriculture, perhaps even language itself. Yet unlike other sciences, astronomy is purely observational. We cannot control the parameters of our experiments from lab benches. Our best technology can send man to the moon and probes to the edge of the solar system. But these distances are vanishingly small compared to the yawning gulfs between stars. So how can we know so much about other galaxies, what they're made of, how many there are, or that they're even there at all? Well, we can start with the first thing we see when we look up at night, the stars. What we are trying to learn is their properties. What are they made of? How hot are they? How massive? How old? How far are they from Earth? And believe it or not, we can learn all of these things simply from the light shining in the sky. We can decipher one kind of stellar message by turning starlight into rainbows. When you look at a rainbow on Earth, you're really looking at light from our sun being scattered through water droplets in the atmosphere into all the different wavelengths that make it up. And when we study the light from other stars, we can create rainbows on demand using not water droplets, but other specific instruments that disperse light. When we look at the scattered light from our sun, we see something strange, dark lines in our rainbow. These lines are the characteristic fingerprints of atoms. Each type of atom in the solar atmosphere soaks up light at specific wavelengths, and the amount of absorption depends on how many of these atoms there are. So by observing how much light is missing at these characteristic wavelengths, we can tell not only what elements are in the sun's atmosphere, but even their concentrations. And the same idea can be applied to study other stars. Make a spectral rainbow, see what's missing, and figure out which elements are present. Bingo! Now you know what stars are made of. But we aren't restricted to just the wavelengths that our eyes perceive. Consider radio waves. Yes, they can bring the Billboard Top 100 to your car, but they can also travel almost unimpeded through space. Because they've come so far, radio waves can tell us the very early history of the universe, from just a few thousand years after the Big Bang. We can also study the infrared light emitted by colder objects like the gas and dust clouds in space, and the ultraviolet light from the hot stars recently born from those clouds. Studying different wavelengths not only gives us a more complete picture of any single object, but also different views of the universe. For this reason, astrophysicists use several different kinds of telescopes, covering the spectrum from the infrared to the ultraviolet to the X-ray, from giant radio dishes to giant silver mirrors to space satellites detecting light that would be otherwise blocked by the Earth's atmosphere. Astrophysicists don't just see the billions of stars among the billions of galaxies in the universe. They hear, feel, and sense them through many channels, each revealing a different story. But it all begins with light, the kind we can see and the kind we can't. Want to know the secrets of the universe? Just follow the light. Light is the fastest thing we know. It's so fast that we measure enormous distances by how long it takes for light to travel them. In 1 year, light travels about 6 trillion miles, a distance we call 1 light year. To give you an idea of just how far this is, the moon, which took the Apollo astronauts 4 days to reach, is only 1 light second from Earth. Meanwhile, the nearest star beyond our own sun is Proxima Centauri, 4.24 light years away. Our Milky Way is on the order of 100,000 light years across. The nearest galaxy to our own, Andromeda, is about 2.5 million light years away. Space is mind-blowingly vast. But wait, how do we know how far away stars and galaxies are? After all, when we look at the sky, we have a flat, two-dimensional view. If you point your finger to one star, you can't tell how far this star is. So how do astrophysicists figure that out? For objects that are very close by, we can use a concept called trigonometric parallax. The idea is pretty simple. Let's do an experiment. Stick out your thumb and close your left eye. Now, open your left eye and close your right eye. It will look like your thumb has moved, while more distant background objects have remained in place. The same concept applies when we look at the stars. But distant stars are much, much farther away than the length of your arm, and the Earth isn't very large, so even if you had different telescopes across the equator, you'd not see much of a shift in position. Instead, we look at the change in the star's apparent location over 6 months, the halfway point of the Earth's year-long orbit around the Sun. When we measure the relative positions of the stars in summer and then again in winter, it's like looking with your other eye. Nearby stars seem to have moved against the background of the more distant stars and galaxies. But this method only works for objects no more than a few thousand light years away. Beyond our own galaxy, the distances are so great that the parallax is too small to detect, with even our most sensitive instruments. So at this point, we have to rely on a different method, using indicators we call standard candles. Standard candles are objects whose intrinsic brightness or luminosity we know really well. For example, if you know how bright your light bulb is, and you ask your friend to hold the light bulb and walk away from you, you know that the amount of light you receive from your friend will decrease by the distance squared. So by comparing the amount of light you receive to the intrinsic brightness of the light bulb, you can then tell how far away your friend is. In astronomy, our light bulb turns out to be a special type of star called a Cepheid variable. These stars are internally unstable, like a constantly inflating and deflating balloon. And because the expansion and contraction causes their brightness to vary, we can calculate their luminosity by measuring the period of this cycle, with more luminous stars changing more slowly. By comparing the light we observe from these stars to the intrinsic brightness we've calculated this way, we can tell how far away they are. Unfortunately, this is still not the end of the story. We can only observe individual stars up to about 40 million light-years away, after which they become too blurry to resolve. But luckily, we have another type of standard candle, the famous Type 1a supernova. Supernovae, giant stellar explosions, are one of the ways that stars die. These explosions are so bright that they outshine the galaxies where they occur. So even when we can't see individual stars in a galaxy, we can still see supernovae when they happen. And Type 1a supernovae turn out to be usable as standard candles, because intrinsically bright ones fade slower than fainter ones. Through our understanding of this relationship between brightness and decline rate, we can use these supernovae to probe distances up to several billions of light years away. But why is it important to see such distant objects anyway? Well, remember how fast light travels. For example, the light emitted by the sun will take 8 minutes to reach us, which means that the light we see now is a picture of the sun 8 minutes ago. When you look at the Big Dipper, you're seeing what it looked like 80 years ago. And those smudgy galaxies? They're millions of light years away. It has taken millions of years for that light to reach us. So the universe itself is in some sense an inbuilt time machine. The further we can look back, the younger the universe we are probing. Astrophysicists try to read the history of the universe and understand how and where we come from. The universe is constantly sending us information in the form of light. All that remains is for us to decode it.
How much can we really know about the universe beyond our galaxy? The Hubble telescope has enabled us to see objects in space as far as 13 billion light-years away. But this still doesn't give us the answers to all our questions. Questions like, what is the universe made of? Which elements are the most abundant? Does space contain undiscovered forms of matter? Could there be antimatter stars? Or galaxies? Some of these questions cannot be answered solely from visual images. But what if we had messengers bringing us physical data from distant parts of the cosmos beyond the reach of explorers or satellites? In a way, we do, and these space messengers are called cosmic rays. Cosmic rays were first discovered in 1912 by Victor Hess when he set out to explore variations in the atmosphere's level of radiation, which had been thought to emanate from the Earth's crust. By taking measurements on board a flying balloon during an eclipse, Hess demonstrated both that the radiation actually increased at greater altitudes and that the sun could not be its source. The startling conclusion was that it wasn't coming from anywhere within the Earth's atmosphere, but from outer space. Our universe is composed of many astronomical objects, billions of stars of all sizes, black holes, active galactic nuclei, asteroids, planets, and more. During violent disturbances, such as a large star exploding into a supernova, billions of particles are emitted into space. Although they are called rays, cosmic rays consist of these high-energy particles rather than the photons that make up light rays. While the light from an explosion travels in a straight line at its famous constant speed, the particles are trapped in extraordinary loops by magnetic shock waves generated by the explosion. Crossing back and forth through these magnetic field lines accelerates them to almost the speed of light before they escape. There are lots of cosmic rays in space, and some of these particles have traveled for billions of years before reaching Earth. When they enter our atmosphere, they collide with the molecules there, generating secondary cosmic rays, lighter particles with less energy than the original. Most of these are absorbed into the atmosphere, but some are able to reach the ground, even passing through our bodies. At sea level, this radiation is fairly low. But people who spend a lot of time at higher altitudes, such as airline crews, are exposed to much more. What makes cosmic rays useful as messengers is that they carry the traces of their origins. By studying the frequency with which different particles occur, scientists are able to determine the relative abundance of elements such as hydrogen and helium within the universe. But cosmic rays may provide even more fascinating information about the fabric of the universe itself. An experiment called the Alpha Magnetic Spectrometer, AMS, has recently been installed on board the International Space Station, containing several detectors that can separately measure a cosmic ray particle's velocity, trajectory, radiation, mass, and energy, as well as whether the particle is matter or antimatter. While the two are normally indistinguishable, their opposite charges enable them to be detected with the help of a magnet. The Alpha Magnetic Spectrometer is currently measuring 50 million particles per day, with information about each particle being sent in real time from the space station to the AMS control room at CERN. Over the upcoming months and years, it's expected to yield both amazing and useful information about antimatter, the possible existence of dark matter, and even possible ways to mitigate the effects of cosmic radiation on space travel. As we stay tuned for new discoveries, look to the sky on a clear night, and you may see the International Space Station, where the Alpha Magnetic Spectrometer receives the tiny messengers that carry cosmic secrets.
On October 4th, 1957, the world watched in awe and fear as the Soviet Union launched Sputnik, the world's first man-made satellite, into space. This little metal ball, smaller than 2 feet in diameter, launched a space race between the US and USSR that would last for 18 years and change the world as we know it. Sputnik was actually not the first piece of human technology to enter space. That superlative goes to the V-2 rocket, used by Germany in missile attacks against Allied cities as a last-ditch effort in the final years of World War II. It wasn't very effective, but at the end of the war, both the US and USSR had captured the technology and the scientists that had developed it, and began using them for their own projects. And by August 1957, the Soviets successfully tested the first intercontinental ballistic missile, the R-7, the same rocket that would be used to launch Sputnik 2 months later. So the scary thing about Sputnik was not the orbiting ball itself, but the fact that the same technology could be used to launch a nuclear warhead at any city. Not wanting to fall too far behind, President Eisenhower ordered the Navy to speed up its own project and launch a satellite as soon as possible. So, on December 6, 1957, excited people across the nation tuned in to watch the live broadcast as the Vanguard TV-3 satellite took off and crashed to the ground 2 seconds later. The Vanguard failure was a huge embarrassment for the United States. Newspapers printed headlines like Flopnik and Kaputnik, and a Soviet delegate at the UN mockingly suggested that the U.S. should receive foreign aid for developing nations. Fortunately, the Army had been working on their own parallel project, the Explorer, which was successfully launched in January 1958. But the U.S. had barely managed to catch up before they were surpassed again, as Yuri Gagarin became the first man in space in April 1961. Almost a year passed, and several more Soviet astronauts completed their missions before Project Mercury succeeded in making John Glenn the first American in orbit in February 1962. By this time, President Kennedy had realized that simply catching up to each Soviet advance a few months later wasn't going to cut it. The U.S. had to do something first. And in May 1961, a month after Gagarin's flight, he announced the goal of putting a man on the moon by the end of the 1960s. They succeeded in this through the Apollo program, with Neil Armstrong taking his famous step on July 20th, 1969. With both countries next turning their attention to orbital space stations, there's no telling how much longer the space race could have gone on. But because of improving relations negotiated by Soviet Premier Leonid Brezhnev and U.S. President Nixon, the USSR and U.S. moved toward cooperation rather than competition. The successful joint mission known as Apollo-Soyuz, in which an American Apollo spacecraft docked with a Soviet Soyuz craft and the two crews met, shook hands, and exchanged gifts, marked the end of the space race in 1975. So, in the end, what was the point of this whole space race? Was it just a massive waste of time? Two major superpowers trying to outdo each other by pursuing symbolic projects that were both dangerous and expensive, using resources that could have been better spent elsewhere? Well, sure, sort of. But the biggest benefits of the space program had nothing to do with one country beating another. During the space race, funding for research and education in general increased dramatically, leading to many advances that may not have otherwise been made. Many NASA technologies developed for space are now widely used in civilian life, from memory foam in mattresses, to freeze-dried food, to LEDs in cancer treatment. And of course, the satellites that we rely on for our GPS and mobile phone signals would not have been there without the space program. All of which goes to show that the rewards of scientific research and advancement are often far more vast than even the people pursuing them can imagine.
Humans have observed comets for thousands of years as their orbits have brought them within visible distance of Earth. Appearing throughout historical records, these mysterious lights that came out of nowhere and disappeared after a short while were thought to be ill omens of war and famine, or the wrath of gods. But recent research has revealed that comets may be even more deeply connected to humanity and our presence on Earth than any of these mythical explanations suggested. When you think of our solar system, you probably imagine the 8 planets orbiting the Sun. But beyond Neptune, far from the heat of the Sun, there is a sparse ring formed by icy chunks ranging from the size of marbles to that of small planets. And thousands of times farther, at the outer reaches of the solar system, lies a spherical cloud of small fragments and gases. Many of these ancient clumps of stardust are leftovers from the formation of the solar system 4.6 billion years ago, while some of the most distant may even come from a neighboring system. But sometimes the gravity from passing planets, or stars, pulls them toward our sun, beginning a journey that can take up to millions of years. As the frozen object travels further into the solar system, the sun grows from a distant spark to an inferno, melting the ice for the first time in billions of years. Gas and steam eject dust into space, forming a bright surrounding cloud called a coma that can grow even larger than the sun itself. Meanwhile, the intense stream of high-energy particles constantly emitted by the sun, known as the solar wind, blows particles away from the comet's core, forming a trail of debris up to millions of miles long. The ice, gas, and dust reflect light glowing brightly. A comet is born, now orbiting the sun along with the rest of the objects in our solar system. But as the comet travels through the solar system, the solar wind tears apart and recombines molecules into various compounds. In some of the compounds that scientists found, first in the rubble left by a meteorite that disintegrated above northern Canada, and then in samples collected by a spacecraft from a passing comet's tail, were nothing less important than amino acids. Coming together to form proteins according to the instructions encoded in DNA, these are the main active components in all living cells, from bacteria to blue whales. If comets are where these building blocks of life were first formed, then they are the ultimate source of life on Earth, and perhaps some of the other places they visited as well. We know that planets orbit nearly every star in the night sky, with 1 in 5 having a planet similar to Earth in size and temperature. If Earth-like planets and the molecules found in DNA are not anomalies, we may be only one example of what's possible when a planet under the right conditions is seeded with organic molecules by a passing comet. So, rather than an omen of death, the comet that first brought amino acids to Earth could have been a portent of life, a prediction of a distant future where creatures made of stardust would return to space to find the mysteries of where they came from.